Hello, this is Miss Moore, and today during chemistry we're going to continue our discussion on electrons. Specifically, we're going to discuss electron configurations and orbital diagrams. Those are fancy words of saying we're going to learn how to assign locations to specific electrons, or to figure out where are they located, where is their specific address on the electron, in the electron cloud. Please make sure today you have available both your periodic table and your orbital diagram handout, which is on the back of your unit conversion table or your reference table. Okay, today's essential question. How are the electrons arranged around the nucleus? Energy and electrons. Energy and electrons are very, very related, and we're going to spend the rest of the unit showing that relationship. Okay, so in nature, change goes towards the lowest possible energy. And it doesn't matter if we're talking about chemistry, if we're talking about electrons, if we're talking about trees or people or DNA or anything. Change goes towards the lowest possible energy. And this is because high energy systems are unstable. Let me give you a quick example. If you've ever seen a little kid at the end of the night on Halloween, they've been eating all that candy and everything. What's that kid like at the end of the night? Chances are the little one is running around like crazy, possibly crying, whatever. Why? Too much candy, too much energy, unstable child. So, in nature, as well as chemistry, unstable systems lose energy to become more stable. So that kid that's running around and crying and being all crazy is really trying to use up energy to become a more stable child. Okay? In the atom, electrons and the nucleus interact to make the most stable arrangement possible. And the most stable arrangement is going to be the one with the lowest possible energy, because higher energy systems are not stable. The ways in which electrons are arranged around the nucleus of an atom are called electron configurations, and that's what we're going to learn how to do today. All right, here we go. Orbital diagrams, which are related to electron configurations. Normally, they're the first step of writing electron configurations. All right, there are 3 rules to tell you how to find the electron configurations of atoms. And just so you need to know the name of the rule. You need to know what the rule says, as well as how to apply the rule. All right, the first rule is called the Aufbau Principle. Aufbau states that electrons enter orbitals of lowest energy first. And if you recall, energy levels are arranged so that the lowest number is the one closest to the nucleus, and that's the one that contains less energy, which means that according to Aufbau, electrons are going to enter energy level 1 first, and when energy level 1 is full, then they'll go to energy level 2, and when that one's full, then energy level 3, and so forth. Okay, next is the orbitals within a sublevel of a principal energy level always have the same energy. What? Okay, that sounds really crazy. Worry not. Write that down, think about it, and we're going to get back to it. And it won't sound nearly as crazy as it just did. Okay, within a principal energy level, the S sublevel is always the lowest energy sublevel. Okay, so just like with the energy levels, the lowest energy is 1, the second lowest energy level is 2 and 3, and so forth. Sublevels also have a hierarchy of energy. So S sublevel has the lowest energy, and then you've got the D. No, sorry, the S sublevel is the lowest energy, and then the P, and then the D, and then the F. Okay, so that's Aufbau's principle. Next is called the Pauli exclusion principle. Pauli says that 2, but no more than 2, electrons can occupy a single orbital. So either 1 or 2 electrons can occupy an S or a P orbital, or truthfully, a D or an F as well. All right, and then we've got another crazy concept here. Chemists believe that electrons spin. And they further believe that if two electrons are in the same orbital, they must spin in opposite directions. Why would that be the case? Well, an orbital is just a little tiny spot. It's like two electrons being shoved up against each other on a love seat. Think about it. Electrons, negative charge. Do negatives like negatives? They don't. They don't like to be that close together. So here's what they do. We've got an electron here, and he is spinning in this direction. Okay. This spinning creates a magnetic field around the electron, allowing a partial positive field towards the top of the electron and a partial negative field towards the bottom of the electron. When the next electron comes and hangs out, sits next to him on the love seat, this electron is spinning in the opposite direction, leading towards a partial negative charge on the top of the electron and a partial positive charge on the bottom. And this arrangement allows these two negative electrons to be close together. Because of Pauli's exclusion principle and this idea that electrons need to spin, when we're drawing electrons in orbital diagrams, we need to show their spin. And trying to draw something like this every time can really end up being sort of a pain. So chemists came up with a short version way to write electrons and show their spin direction. And we do that by showing an up or a down arrow. Okay, so this is showing this electron is spinning in some certain direction, I don't know, and this one's spinning in the other. And the last rule is called Hunds Rule. And Hunds Rule is the rule that's most often broken when trying to draw orbital diagrams. So keep that in mind. Be careful with this one. So when electrons occupy orbitals of equal energy, one electron enters each orbital until all the orbitals contain one electron with parallel meaning the same, spin. Then the second electrons go by and add into each orbital so that their electrons are paired with the first electrons, meaning opposite spins. One thing that helps me remember Hunds Rule is just sort of think about people. If a handful of people are in a room, say a living room or something where there's a bunch of couches, usually the first person sits down, and when the next person comes to sit down, they don't sit right next to the first person. Nobody likes to be squished up. They're going to spread out around the room. As more and more people arrive to the room, though, that's when the people need to start pairing up, squishing together on the couches. It's the same with the electrons. They prefer to be separated. And as long as they don't have to exert more energy to be separated, they'll do that. So, as long as the orbitals are all within the same amount of energy, they're going to spread out, and they won't start squishing up or pairing up until they don't have a choice. All right, it's just about time to start learning how to draw orbital diagrams and learning how to apply these three rules. All right, so now let's talk about your orbital diagram handout, how to read it, how to use it. And I guess the first thing we should do is try to explain all of these little symbols and stuff here. So the box I just highlighted, we'll discuss that to begin with. So I'm going to redraw it in a little bit of a different direction. So we've got 2. We have a P, and we've got some boxes here. So this 2 is representing the energy level. Remember that energy levels are represented by numbers. The P is representing the sublevel. And the boxes represent the orbitals. And as we can see, a P sublevel has 3 orbitals. And then the electrons would then be arrows in the orbitals. Okay, and you'll notice that I just followed Hunds Rule. I put 3 electrons in energy level 2, sublevel P, but only 1 in each orbital, and then I could go back and fill in more. So the red are the electrons, and a couple other terms you should know is this here. Those are paired electrons because they're a set, right? You've got one spinning in one direction, one spinning in the other direction in the same orbital. Those are paired electrons. These two here are unpaired electrons. While it's true there's 2 of them, so you could think of them as a pair, they're not paired, right? It's like if just because I have 2 shoes, I may or may not have a pair, right? I might have a blue tennis shoe and a brown work boot or something. That's 2 shoes, they're not a pair. Same thing with the electrons. 2 doesn't necessarily mean a pair. A pair of electrons is when you have 2 electrons in the same orbital with opposite spins. Okay, so one more time. These guys here are paired, and these 2 here are unpaired. All right, so now let's try to do this. I take it back. We've got a little bit more to go over here. First of all, I don't know if you can see this arrow here. This is denoting increasing energy. So the energy is getting greater as you move up. So following Aufbau's rule, that would mean that the electrons would start in fill up energy level 1, sublevel S. After that was full, they would then proceed to energy level 2, sublevel S. And from there, they would proceed to energy level 2, sublevel P. And when energy level 2 was completely filled, they would proceed to energy level 3, sublevel S, and then energy level 3, sublevel P, and then energy level 4, sublevel S, and I'm going to stop. Hopefully you get the point. Okay, now let's try to do this. Okay, we'll start by writing an orbital diagram. And from there, I'll show you how to write an electron configuration. Okay, so we'll use, as our example, we'll start with lithium. That's a pretty easy one. So if you could look at your periodic tables and tell me how many electrons lithium has. Lithium has 3 electrons. So now we got to figure out where can those 3 electrons go. Remember, we're starting at the lowest energy level, which is 1s, and the first electron will go into 1s, as will the second electron. The third electron will then go into 2s. So to write the orbital diagram, we're going to write 1s, and I usually just draw a line instead of a box because I find it easier. And we'll put 2 electrons in 1s and 1 electron in 2s. That takes care of all the electrons in lithium, so we've just written the orbital diagram for lithium. So now, how do we write the electron configuration? Well, the electron configuration is almost the same as the orbital diagram, gives you almost the same information. The only thing electron configuration leaves out is the actual orbitals. Okay, it shows the energy level, like the 1 or the 2. It shows the sublevel, this case S and S, and it shows you the number of electrons, but does not show you the exact orbitals. So we're going to write energy level 1, sublevel S with 2 electrons. Energy level 2, that's not a 2. Energy level 2, sublevel S with 1 electron. And this is the electron configuration for lithium. Let's try another one. Let's try nitrogen. How many electrons does nitrogen have? Nitrogen has 7 electrons. Okay, so let's go back to our orbital diagram handout and see where those electrons are going to be located. Okay, so we're going to start with 1s again. We can put 2 here. Then we'll proceed to 2s, where we can put 2 more. That's 4 electrons. We need space for 3 more electrons, which means we're going to have to go up to 2p. So we'll start with 1s, and we can put 2 electrons in there. And then we'll go to 2s, which will have 2 more electrons, and then we'll go to 2p, which how many orbitals does p have? P has 3 orbitals, so we need to draw all 3. And then following Hunds Rule, the anti-squishy rule, remember they don't want to be squished up, we're going to put electrons in individual different orbitals with the spinning in the same direction. And so there you go, and that gives us our total of 7 electrons. So now, to write the electron configuration, we're going to have 1s2, 2s2, and 2p3. So there is the electron configuration for nitrogen. Last one. Let's try oxygen. This time, if you could do me a favor, hit pause. Try to do the whole thing by yourself. Hit play, see how you did. Okay, so oxygen has 8 electrons. So we can put 2 here and 2 here. That makes 4. And we need 4 more, which can go here. So we're going to use 1s2, 2s2, and 2p. So 1s with 2 electrons, 2s with 2 electrons, and 2p, 3 orbitals. We need 4 more electrons. So 1, 2, 3, and 4. So the orbital diagram for oxygen looks like that. The electron configuration would then be 1s2, 2s2, and 2p4. And as a quick review, what do we call those 2 electrons versus those 2? Well, the first 2 are called paired, and these guys are called unpaired. Abbreviated configuration. So abbreviated configuration is kind of nice. It's a shorthand way to write electron configurations. What you do is you write the symbol for the noble gas near just before the atom, and then you just write the valence electrons. So you don't have to write every time 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, and so forth. Okay, so let's try one. Let's say I wanted to write the electron configuration for sodium. So sodium is 1s2, 2s2, 2p6, 3s1. The noble gas, this is the long form, normal. If we wanted to write the abbreviated version, we go back and find the nearest noble gas before sodium. Sodium is element number 11. Neon is the nearest noble gas before sodium. So we would write neon 1s, no, not 1, neon 3s1. So what it's saying is sodium has an electron configuration just like neon. There's neon's electron configuration. And you just add a 3s1 to it. So this is abbreviated configuration for sodium. Let's try another one. Let's say I wanted to do chlorine. So chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. If we wanted to write the abbreviated version, the nearest noble gas before chlorine is still neon, right? So I'm going to write again neon, and chlorine has the exact same electron configuration as neon until you get to the valence electrons, which is 3s2, 3p5. All right, one more topic to go. We're going to talk about something called exceptional configurations. So a few of the atoms in the D block do not follow the Aufbau principle. Remember, Aufbau said that electrons fill the lowest energy levels first till they're full and then move up and up. Okay, so remember that atoms want the most stable configuration. I mean, that's the whole point. And normally, in most cases, the most stable configuration is when the electrons are in the lowest possible energy level. However, there are two other cases which make things very stable. If you have a completely full energy level, or if you have half full energy levels, like completely, exactly half full, not partially full, but half full, okay? So there are two times when this could happen. One time is if you end in, if you're doing electron configuration, you end in S2D4. So let's do that real quick. And I'm actually going to do it with the orbital diagram. It's a little bit easier to see. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, so this is not the most stable because you've got a one full sublevel and then a partially full sublevel. But with the movement of one electron, if I were to take this electron and move it to here, we now have a perfectly half-filled energy level. Okay, so I'll get rid of this guy. And you have a much happier atom. Okay, so anytime you're doing electron configuration or orbital diagram and you get the answer something S2, something D4, then move the electron to make it, what do I have D1 there? Should be S1D, change that, change this to D5, okay? That's a complete, that's when you have a complete half, how do I say this? You have a completely, perfectly half-filled energy level. Okay, the next time is if you have S2D9. The electrons are actually happier, the atom's actually happier if we have a full D to just jump an electron over. So this is just something you sort of need to memorize. All right, that's it for today. Have a good one.